Welcome. In this video, we're talking about multiple covalent bonds and how that changes the type of covalent bond between the two atoms, between the two nuclei. So there's actually two kinds of covalent bonds. There's a sigma bond and there's a pi bond. And when there's only one pair of electrons being shared, it will be just a sigma bond. But if it's a double or triple bond, when there's two or three pairs of electrons being shared, then they have to form pi bonds for that second and third bond. And that's because the sigma bond takes the center, takes the best spot, kind of like, if you're in a movie theater and you get the center seat, the best seat there, everybody after you is going to have to take a seat maybe close to you, but not in the exact same place. And that's kind of what happens with the sigma bond. The first pair of electrons shared is the sigma, or the simplest, the single bond. And every pair after that then forms what we call a pi bond. So a sigma bond forms by head-on overlapping between the atom's two atomic orbitals. So if you take your two hands and you slowly move them close together until your two thumbs are touching, that's kind of what happens with a sigma bond. The two nuclei move close enough that the electrons are going to share are in the center between the two nuclei, and each atom now thinks it's gained an electron. The sigma bond is always stronger than the pi bond because it's in the center. Okay, again, it's in the best place, and it's always the first covalent bond to form. So single bonds and a double or triple covalent bond will always have a sigma bond, and now if another pair of electrons gets shared, then they'll have to overlap around this sigma bond, and that will form a different kind of bond known as a pi bond. So the orbitals of the atoms overlap at the ends, and again, kind of like moving your hands together until your thumbs overlap each other. That would be your sigma bond. A sigma bond forms first since it's easier to form physically. It's just easier when those two just have to move close enough to overlap. But then the second and third bond have to form above and below it. So a pi bond is where the lobes of one atom's orbital overlap lobes of another's. And in this case, I can see I've got a p orbital here and a p orbital here. And in order for them to share each other, this one has to flop this direction, and this one has to flop this way. And so then you end up with this common space. But this was these two orbitals here, and they kind of flop toward each other. And the same thing happens here. They have to get close enough so they can flop over to each other, and now they share another pair of electrons. Okay? So again, it's kind of like a hot dog being the sigma bond, and now the bun is above and below it, and that's the pi bond. But that pair of electrons has to hang out above and below. And what if you had a triple bond? Well, then it would be like adding another bun in front and in back of this thing. So I can't draw three-dimensionally very well, but it'd be like having a double bun on there. So formation of sigma and pi bonds. Here it's a little easier to see that the red here is, this is when the very first bond right here, this is the sigma bond where the ends just move together in the same plane, and they share one pair of electrons, and that's the sigma bond. And then when they move close enough that now this part can overlap, now I've got the donut or the bun above and below. Now this is my pi bond. So here I can just see the sigma bond down in here. There's my sigma bond taking up the best place, and here's my pi bond around it. And the top and bottom together, both parts of the bond, make up the pi bond. So let's talk a little bit about the strength of covalent bonds. Covalent bonds are generally weaker than ionic bonds, and that's because electrons aren't transferred, they're just being shared. So you don't end up with these oppositely charged ions to help hold things together. It's simply two nuclei pulling on the same pair of electrons. So this pair of electrons is kind of suspended between the two nuclei. So covalent compounds are going to have different properties since they have a weaker bond than the ionic. So what's stronger, a single, double, or triple bond? Well, it's kind of what you would expect. A single bond is going to be the weakest, and a triple bond is going to be the strongest. And a couple things affect this. One is the bond length. A shorter bond means a stronger bond because the electrons are going to be closer to the nuclei. We already know this, that smaller allows the positive and negative to hold more tightly. It's like having your magnet closer to your fridge with fewer papers in between. So sigma bond is able to get the closest, but as you form a double and triple bond, a single bond doesn't have to get that close until they're overlapping. But now if you want to share a second bond, it has to move closer. And if you want to share a third bond, you have to get really close, which is why we don't see quadruple bonds, because the nuclei would be on top of each other. There'd be too much repulsion there. You just can't get atoms that close. So again, my shortest bond is the triple bond, and that's going to be the strongest. And my single bond is going to be the longest and weakest. And think of it like pencils or, twigs. If you're snapping them, longer is easier to snap. Shorter makes it harder and harder. So there's a name given to the energy needed to break a covalent bond. Remember, with ionic bonds, we call it the lattice energy. Well, with covalent bonds, we call it the bond dissociation energy. Dissociate is just the opposite of associate. Dis means distance. So to put distance between two atoms or to break that bond is the bond dissociation energy. And because atoms come in different sizes and share 1 to 2 to 3 pairs of electrons, the energy needed to break covalent bonds depends on the two atoms. So hydrogen, which hangs out with itself to form hydrogen gas, or H2, takes a different amount of energy to break apart than F2. Even though they're both small atoms, they're not exactly the same atoms. The bond dissociation energy is also equal to the energy that was released when the bond was formed. So when atoms bond together, they release the extra energy because they become more stable by bonding together. And then that same amount of energy is needed to break them apart. A shorter bond length will mean more energy to break it apart, because remember, shorter is stronger. So it's just logical, it will take more energy to break apart. Why do we care? Because it allows us to predict the energy that's stored in a fuel or in foods. Foods are considered a fuel, but lets you know how many calories are there, whether you're burning it for your own personal energy or to heat your home or to drive your car. So there's all kinds of reasons why we'd want to know the energy in a certain molecule. So the last thing to talk about is this idea of endothermic and exothermic reactions. In an endothermic reaction, more energy is used to break the bonds than is used or released to form the new bonds. So it means energy is absorbed. So endo is just like it was back in biology. Endo means inside, exo means outside. So endo means energy is going into your products, or energy is absorbed during the reactions. So it means your products have more potential energy, but they're less stable. So let's take a look at this diagram here. If I have my reactants with X amount of energy, so my energy is over here, it's increasing as we go up. So if I look, I can see my reactants have less energy than my products. And then I've got this funny shape in the middle here where some stuff is going on. Well, what's going on here is energy is being put in. There's energy in to break up the reactants. We have to break the bonds of the reactants apart, just like if you take your Legos apart before you can build new Legos. And then up here, this is where, I like to say the magic happens, but this is where the reactant particles collide with each other to form the new products. So over here, energy gets released to form new bonds, or in other words, our product. So there's two parts to every reaction. There's the bond breaking part, which has to happen to the reactants so that you can use those atoms to make something new. And then there's the bond making part. And the bond breaking part always needs energy or energy in, and the bond making part always has energy out. Well, one of those is going to take more energy, either the bond breaking or the bond making. If it takes more energy in to break the bonds, then the products are going to have that extra energy, and we call it endothermic. On the other hand, in an exothermic, there's more energy released, so I can see here that my energy released, and energy you can abbreviate NRG, just like it sounds, energy. So this is the energy released in bond breaking, and that's more than the energy in, or the energy absorbed, in the bond, I'm sorry, this is the bond making over here. So as energy released in the bond making is greater than the energy that was absorbed for the bond breaking. So you have to break before you can make. So the difference between those are what we call the enthalpy, or the heat of energy of the reaction. And if it's net energy in, we say it's a positive gain in energy. And if it's net energy out, it's a loss or a negative value. But looking at this chart, I can tell my products are more stable because they have less energy, whereas with the endothermic, my products are less stable because they have more energy.